within AI systems and a case for design diversity. And Preface James Evans is a professor at the Department of Social Science at the University of Chicago, and he's the director of the Knowledge Lab. His research focuses on the collective system of thinking and knowing, ranging from the distribution of attention and intuition. And the origin of ideas and shared habits of reasoning to processes of agreement, accumulation of certainty, and the texture of understanding. Professor Evans is especially interested in innovation and the role that social and technical institutions play in collective co-creation and discovery. Let's welcome Professor Evans.
Thank you. Hi, friends. Let me share my screen here. Can you see that?
Yeah, thank you.
Okay, great. And how long do I have, just so that I respect the other speakers?
Yeah, I think you have 30 minutes, and you can leave a few minutes for QA.
Okay, great. So I'll plan to talk for about maybe 23 or 24 minutes. I'll set a soothing chime to remind myself. Well, I know this section is on personalizing, on really responsible personalization in artificial intelligence. And I'd like to flip it around here and really talk about personalizing responsibility in the context of artificial intelligence within these systems, and the case for designing diversity. And I'll kind of suggest why I think that's relevant for some of the applications that I think will be critical for AI's biggest assistance for human capacity or augmentation of human capacity. As was mentioned, I run a center called Knowledge Lab, which is really focused on large-scale data, machine learning, and intelligent crowdsourcing, enabling us to understand the nature of human knowledge, represent it, and really transform it. In this, we're interested in understanding how systems think and how innovation occurs as a system, and how we can think better collectively. I've spent a lot of time over the past 20 years pushing arguments about how to use the full scientific imaginary and models in order to improve the scientific process in places like Science and Nature, and at funding organizations around the world. I come from sociology and have really been pushing computational social science with colleagues like Chris Bale, who was mentioned in the last talk, and run a journal of social computing out of Tsinghua University with IEEE. So, and then a final thing, which is the most relevant, I think, for this audience, is that I recently started an Institute for Trusted Intelligence in Society, in which we're focused on exploring human values underlying trust through conceptual analysis, adaptive experiments, and active learning, and the interaction of values, to the enabling of human AI communication to enhance the trust of humans of AI systems through improved human specification, as through counterfactuals, through mechanistic explanation, and through uncertainty quantification. And then finally, to ensure complex competence, to not just improve trust, but trustworthiness, so to improve warranted trust through ensuring complex competence, which is to say the competence of these systems to satisfy the particular personalized range of values that individuals have, through robust optimization, deep audits of these systems, benchmarks, and ultimately the building of AIs to monitor other AIs in an algorithmic system of checks and balances. And we're looking at this both in the context of self-driving, assistive robotics, and a number of enabling AI contexts in which decisions are recommended by artificial intelligence systems. So in my personal research, a lot of what I've done up to this point is to try to understand innovation sufficient that we can automate innovation, which is to say that if we can't automate innovation, then I'm dubious that we understood that innovative process in the first place. And I'd like to pose you the question to begin with of this idea of what kind of artificial intelligence do we want? What kind of AI do we want? Do we want, for some tasks, do we want an Alan Turing-inspired imitation game style of intelligence, where human intelligence is the standard, right? So is 1950 ideal in computing machinery and intelligence? Or even taking it a step further, if Turing was focused on human outcomes, Arthur Samuel's notion of machine learning from 1959 was focused on human moves, right? How do we get a program to really look like a human in action, as well as achieving a human-like outcome? This was the notion underlying John McCarthy's AI conference bid in 1955, which began in the summer of 1956. So this idea of kind of humanoid AI, if you type in artificial intelligence to a browser, it's going to come up with this human imaginary. These are pictures, artistic renderings. When people think about artificial intelligence, they're thinking about humanoid intelligence. But I would just argue that with 7.5 billion humans on Earth, this is neither the most ethical nor the most efficient computational intelligence investment, especially in cases of competition or indirect competition, where we're trying to compete against each other for scientific advance or cultural excellence. An alternative vision for AI emerged really the same year. Interestingly, in 1955, William Ashby wrote an introduction to cybernetics in which he coined the term amplifying intelligence, which kicked off 1960s use by Doug Engelbart of augmenting human intellect, and J.C.R. Licklider, who really sponsored at ARPA the internet, this idea of man-computer symbiosis, right? So an idea of, instead of just trying to artificially replicate human intelligence, we're going to amplify or augment it. Now, for them, that meant unmediated manipulation of information. So we're going to try to accelerate your thinking through interfaces, right? And so you can see this is, in this particular Engelbart demonstration, we've got the mouse demonstrated for the first time. We've got file systems. We've got screens. The modern version of this would be cochlear or neural implants, right? Or an EEG helmet that would allow you to immediately modify the information that was available to you. But even though this is useful, it's productivity enhancing, it's also necessarily incremental, right? It can really only act and move at the speed of your individual thought. What if you wanted to complement your intelligence and really think differently, think better collectively? So I'm going to talk about the importance of personalization in the context of designing ensembles of complementary intelligences that can complement not just anybody and everybody, but complement you as an individual, that can facilitate and provide personalized support for expanding and augmenting your intelligence relevant to a complex and often competitive task. This insight comes from what I'll call the wisdom of crowds, right? And not just any crowds, but here we're going to talk about the wisdom of innovating crowds in the context of science, technology, cultural products, business. And so I'm going to go through three kind of chapters, very brief chapters. I only have 15 minutes left in my remarks, and then I'll take some questions and answers from you. I'm going to talk about diverse crowds are characterized by something I'll call collective abduction, bridged difference. Two, how connection and conformity is associated with reduced replication and impeded innovation. and how AI that designs diversity beyond human limits, that's personalized to your human capacity, can accelerate and punctuate advance and facilitate not only trust, but trustworthiness. And together, a kind of a warrant to trust between humans and machines that are working together. So how do innovative systems think in the first place? Well, I'll give you a case, an example. In this case, I'm going to try to predict all of next year's papers, right? And so I'm going to build a generative hypergraph model of papers. A hypergraph is a set, and in this case, the set will contain keywords associated with a particular investigation. I'm going to do that by building a surface, right? A high-dimensional manifold. This is about, through cross-validation, about 40 dimensions, that contains all the keywords associated with papers in a given domain, like biomedicine or the physical sciences. And then I'm going to wrinkle that manifold. I'm going to tune it so that I do a Poisson draw of the manifold, which takes into account the proximity of those keywords in its space and the relative popularity of them, or their cognitive availability to individuals in the space. The product of those two things is going to condition that draw, and I'm going to maximize the probability of that hypergraph conditional on those parameters, those thetas in that space, and the popularity of those elements. Okay? And what this is going to allow me to do is produce a measure of novelty, right? So the least expected combination of elements in the next period is going to be associated with their surprise and attention in the scientific or cultural space. When I look at this in the context of biomedicine, the physical sciences, and invention more broadly across about 50 million research products, I can identify very rapidly, for example, well, first, it predicts, our AUC in prediction of papers is about 0.95. So we can predict most papers, but the papers that are unexpected or improbable under this most probable model are really unexpected papers, like this green paper here that combines really distant. This is a three-dimensional rendering of the space of keywords in the biomedical sphere. This paper connects what was previously thought to be exclusively animal functionality into plants, which really surprised the research community. It looked at trypsin in the context of plant proteins, thioredoxin H using chromatography and high pressure, under high pressures. When we do this, what we find is that the papers that are the most novel in terms of their combinations of contents or keywords and their combinations of sources or journals, that this novelty itself predicts the likelihood of being a hit paper, being in the top 10% of citations. So you can predict almost 60% of that likelihood of being in the top 10% of papers, independently of any metadata information about individuals or the places that these papers were published, or even if they were published at all. So basically, the surprise, the novelty, ends up being the thing that drives attention in the scientific space. And it turns out it's true for every case that we imagined it and examined it. Moreover, what's driving that surprise? So is it individuals who have an unusual background? No, not really. That would be career novelty. Is it teams that put together novel combinations of people? Not really. It's expeditions of people who move from one part of the space to another. So you can think of it as radical insight coming in conversation between insiders who own a journal, for example, and outsiders that are coming in and traveling across the scientific space with skills and talents that were unaware and unexpected within that context, even if you get low novelty and in the context of careers and teams, but high novelty in the context of these expeditions, it dramatically increases the likelihood that you will discover something that's novel and that ends up being of high impact in the scientific space. Now, it turns out that this is historically the thing that most characterizes modern science in general. So from the 1900s until the mid 1950s, we see this increase in the entropy over sources. So the difference in the journals, for example, that you draw on goes up and really reaches its peak in the 1960s. And then from the 60s on, we basically have that's the thing that characterizes modern science, is that increasingly our problems are solved by people that are outside of our own space. And it turns out that this novelty is important not only in the scientific space, but also, as our last speaker talked about, in the political space. So increasingly in the United States, but also in many other countries, there's been this increasing disconnect between groups of people on the left or the right or across other poles in society, in terms of their exposure to information. So this is a paper in which we showed that basically different people with different political opinions in the United States, that consume political information associated with the left and the right, the conservative and the liberal poles, are increasingly selecting information in the scientific space, which is also different. Now, the question is, what's the implication of that for working together? And as I suggested earlier, that augmented diversity should mean that if we can find ways to work together, because we're exposed to different information, that our collaborations will be improved in their quality. And this is exactly the case. When we looked at individual annotations of Wikipedia articles, and we use those to ascertain individual political positions, and it turns out that their likelihood of contributing bits to conservative versus a liberal page predicted about a third of their self-described ideology and their likelihood of voting in a particular direction. That when you had greater diversity in politics, which is to say polarization, that was associated with much higher quality, independently assessed Wikipedia articles. And those articles were found in the context not only of politics, but also social issues and science, which would be expected to be less polarized. So because of different people collaborating with different kinds of backgrounds together, in this case, even though they had different political backgrounds, the pages that they worked on together were assessed by people who didn't understand how those pages were constructed as being of higher quality. So on to the kind of the second chapter, another just demonstration of the importance of novelty before I get to the case that shows how we might design AIs that do this in a personalized and responsible way. There is this thing that's increasingly called, really since 2005, the replication crisis in science. And it shows that, in pharmacology research and genetics research and psychological research, research across the board, that there are an awareness that many of these findings in science don't actually replicate. And when we lined up findings from the literature, in this case, we took a high throughput approach to analyzing the social structure underlying replicability. So we took hundreds of thousands of claims inside the literature, we linked them with high throughput experimental results, and we found systematically that findings from decentralized communities, from more diverse communities, were much more likely to replicate. So when you had less centralization, right, then you saw a much greater probability of replication. When you have greater social independence, which is to say social diversity, separate teams that aren't connected by researchers directly or indirectly, again, a much higher likelihood of replication. And the reason is because when everyone is the same, then you're not performing many independent experiments, you're performing many dependent experiments. There may be 50 experiments, but it really amounts to like 1.5 independent takes on the problem. And it turns out, we know that this works because in a recent Nature Machine Intelligence article, when we take this into account, we do much, much better at predicting those findings that are going to be robust in future experiments. And we can redesign our empirical approach to analyze those by searching for diversity in the space and system. So the question is, can we take these principles and can we design diversity, design personalized diversity with AI to increase collective imagination and to increase individuals' trust in the artificial intelligences that they collaborate with, trust that they will enable them to improve their performance. And this work is with a colleague, Jamshid Surati, a postdoc in Knowledge Lab. So this was an interesting paper that was published about 3 years ago. It basically used a relatively simple auto-encoding neural network device to identify individual papers. It basically auto-encoded these papers to identify new materials that had valuable energy-related properties like thermoelectricity or ferroelectricity or photovoltaic capacity. Photovoltaic capacity is the capacity basically for these materials to collect and preserve and store light energy. And so basically, this machine built on the scientific literature had about a 0.4 precision, which means about 40% of those predictions about which materials had which properties would be discovered to be true over the course of the next 20 years. And what we did was we did something a little bit different. We said, hey, what if we identified the inferences that are most cognitively likely? Okay, so we identify those inferences which are most likely to be made by individuals. So these heat maps are for thermoelectrics, ferroelectrics, and photovoltaics, and the density in the heat map corresponds with the number of people who sit between that property and that material. So we make a series of predictions which are what I'll call expert aware, right? They're aware of the existence of experts, and they provide something that sits on that space that is the most likely that experts will come up with. This prediction of cognitive available inference dramatically increases the likelihood that our AI predicts the outcomes. So rather than embedding the literature, we're embedding random walks through the hypergraph of this scientific space, right? So we walk from a property to a paper with the property to a person who investigates that property, to another paper by that person, to a material by that person in that paper, to another paper with that material, et cetera, et cetera. So we run, millions of random walks over this space, and more than double, we improve our prediction rate, our hit rate of those things that will be discovered from 100 to 500%. So in the context of photovoltaics, we're really not making a bad prediction. Every prediction is actually discoverable in the scientific system. And this allows us to basically avoid scientists, right? In addition to following scientists, we can turn the dial the opposite direction and avoid those scientists. And it turns out that when we do that, we improve our prediction. These alien predictions basically are more complementary to human intelligence. If they're discovered in the scientific space, it's years further into the future than it would be otherwise. And it turns out that they're actually more valuable. They're more likely to have these properties. For example, thermoelectric, photovoltaic, ferrovoltaic. Even when we look at it in the context of repurposing drugs or even COVID vaccines, we get a really big boost in the relative efficacy of those predictions. And the reason is because they're diminishing marginal returns to theory. What this allows us to do is to identify, if a person is looking for predictions, what are the space of things that they're investigating, and what are the things that are the most likely to complement their existing intelligence and awareness, right, as a function of the position they are in the scientific or cultural space. So, how can we advance technology and enterprise through, in this case, personalized AI provocation to build ensembles of diverse intelligences, which will allow those individuals to perform at high levels? I just will mention one other case in point, which suggests the importance of personalization. So, for example, in the context of really using artificial intelligence to accelerate the research design process, recently we've used the active learning cycle of building a surrogate model, which then leads to a sampling or acquisition function frame, which leads to the collection of more data. So we've used this as an active design to improve automated experimentation. And we use this automated experimentation for the genesis of teams performing different kinds of tasks. And when we do this, we find that they really discover very different kinds of diversities, right? Diverse combinations of task members and their cognitive skills in order to perform these different tasks. So it's not just personalization for a person here now, it's personalization of a team for a person for a task, right? That's the thing that becomes worthy of trust, right? Worthy of the performance that we expect of these artificial intelligences, in this case, to recommend systems that are going to facilitate our performance in the world, our improved performance in the world. So I'm just going to close by suggesting that, trust in artificial intelligence conditions the likelihood that we will use artificial intelligence in value increasing activities in the world. And that we need to understand the precise and particular values underlying trust, their trade-offs with one another, and the situations under which people have different demands for those AIs, so that we can increase our personalization of the artificial agents for the purposes that are put to them and the context to which they're put, so that we can increase not only trust in these AIs, but calibrated or warranted trust that is respected by the value that these AIs produce for us. And so with this, I'll just close, suggesting again that most of the ways in which I've been talking about diversity in the context of this talk have been about cognitive, perceptual, and experiential diversity, but these map on also to identity diversities that we're aware of, gender diversity, ethnic diversity, etc. So I think I've got like 2 minutes for questions. If we have, if there are any questions, I'd love to field them.
Yeah. Thank you, Professor Evans. Thank you for a great talk. Yeah. Do we have some questions from the audience?
Actually, I have a question. Yeah. Thanks, Sam, for the fascinating talk. And I learned a lot, especially I like the part of using academic graph to learn innovation. So I have a question about actually the topic of this workshop. We are working on interdisciplinary research for responsible AI. And the previous panel, we mentioned that AI itself is interdisciplinary. So do you see how this was studied in your research? Have you, I think you studied the size of the team and how to build a team for innovation. What's your comments on this?
Yeah, no, that's. I mean, I think this is another case in which we found that increasing the relative diversity of members of the team and decreasing the size and the hierarchy are associated with improvements in the likelihood that the teams will generate things that are novel and disruptive. Large teams tend to be expensive. And because they're expensive, they almost always hedge against failure by picking successes from yesterday, right? So big, AI systems or, big scientific results that occurred yesterday with lots of attention, maybe in Science or Nature or in NeurIPS or iClear, and then they build on those. And the reason they do that is because they know they're like movie production studios that are going to predict and basically put money on like Transformers 9. Transformers 9 is going to be a terrible movie whenever it comes out, but they know that it's going to get the same receipts as Transformers 8 minus Epsilon. In the same way that if you build on a big hit from yesterday, you're going to get the same eyeballs minus an increment. So I think if you're trying to do something disruptive and innovative in the space, then then we have to avoid doing this thing, which becomes very natural for large-scale industrial teams, which is to basically build on yesterday's hits and create. We basically move scientific development into like the space of blockbuster films, where we're just, we're just, kind of increasing the likelihood that the same ideas are getting play. We're reducing the likelihood of surprise.
Yes, thank you for the great suggestion. That's very insightful. Yes, thank you.
Sure. Thank you.
Thank you, Professor Evans, for giving us such a great talk at Deep Night.
Yeah. Okay, thank you. Yes, it's very early here in Utah, where I'm at today. So, anyway, have a great evening. Thanks so much.
Yeah, thank you. Bye.